So today it's my pleasure to welcome Dr. Donald Blankenship. He is a research professor here at UTIG. His interests are in dynamic processes below, within, and surrounding terrestrial ice sheets that control rapid changes in global sea level, as well as subice habitability across the solar system, particularly at Europa. He's been PI and director for many multi-year Antarctic exploration programs incorporating aerogeophysical platforms. He has specialty in integrating various instrumentation tools to produce the rich data sets required to address various hypotheses for the evolution of Earth's ice sheets and ice shelves, as well as understand the formation of Europa's dynamic surface geology and terrestrial analogs. He's been an active member in multiple NASA-sponsored science definition teams going back to 1998. He's currently the principal investigator for the radar for Europa Assessment and Sounding Ocean to Near Surface Horizon instrument, which will be flown on NASA's flagship Europa Clipper mission, launching hopefully in October of this year. So with that, I'll hand it over to you.
Okay, test. Hi, Sean. Test 1, 2, 3. Can everybody hear me on Zoom 2? I don't know where the camera is. Yeah, that's okay. We'll get going.
They said yes.
Yeah.
You're good.
Okay, and that review makes the first few slides easier. I'm gonna tell everybody about going to Europa. We're finally there. I've been working on this for about 25 years, and hard for the last 10 years. And so the goal here is to let you know how we go about deciding what to do on Europa and how we get ready to go to Europa and do it. It's a habitability mission. And so we'll go through all the details of why it's such a high priority for habitability. I'm the Lone Ranger here for giving this talk, but here are my 107 co-authors for the Space Science Reviews paper that just got accepted, which means that's your formal stamp that son of a gun, you guys are done, you built it. There are about 70 engineers, 25 co-investigators, and then about 10 postdocs and graduate students who basically did most of the work. And so where do UT fit in all of this? This is a breakout of the folks. Yeah, I get to be PI, so I'm herding the cats. Duncan, these people are all UTIG. Duncan Young helps handle JPL with me, and he's responsible ultimately for the soundness of the data. Scientifically, we work together on shallow, brittle, icy things. Cyril Grima is near surface, and Krista Soderlund is the circulation modeler for Europa Ocean, and she works on accretion at the base of the shell. All that stuff will make sense. The important part down there is the science verification validation team. The unsung heroes of this whole mess. These are my PhDs and postdocs who basically were trained at UTIG starting 10 years ago, and now they're off occupying places at APL and JPL, and they will ultimately be responsible for implementing the science strategy and the tactics of mission operations. This mission remembers a multiple. Talk about this more. It's multiple flyby mission, and so we're bringing the capacity to ask questions in the first 30 kilometers in depth of icy worlds in the outer solar system. We've been limited to 3 microns for icy worlds in the outer solar system to this point, and so now we can dial up what we want to see for hypotheses. So it took a lot of science validation and science verification to get to that point. That's what that paper is all about. It's only 117 pages. It's a quick read, but it's all in there. These folks did it. It's just amazing. So that's where we are. Let's just keep going. Now let's get to Jupiter. These are the Galilean satellites, as first seen by Galileo. Remember, the Galileo mission ended in 2003 and gave us these beautiful pictures of Io, Europa, Ganymede, Callisto. They're in resonant orbit, so Io takes about a day, 1 3/4 days to circle Jupiter. Europa's 3.5, Ganymede's 7. The most interesting, and the thing I should mention is that we were supposed to be the next thing in the system, but Juno was off at Jupiter measuring the ionosphere. And Scott Bolton, being the incredibly creative PI he is down at SWIRI, convince them to let the orbit go elliptical, and so he's been flying by the icy moons. He's got a pass of Ganymede, a pass of Europa, and I think they got 3 passes of Io. And so that would finally, it's really kind of nice. You know, when you take 10 years to basically, you know, go through the literature and come up with all these theoretical hypotheses and prove that you've made the right instrument, not only did you make it, and then that you made the instrument right, but then all of a sudden this other mission comes along and it validates some of the assumptions you made. So it's not a bad thing. Everyone was freaking out, you know, that Juno was going to steal their science, and that is just not the way it's turning out. It's actually really, really nice. What it's doing is constraining the point models that we have for Europa's subsurface. And it's so open, you know, the instruments on Juno can't possibly give convergent answers, but what they can do is knock the parameter space down for what we assume when we're going to Europa. And that means that as we design the flybys, we can be much more specific in the questions we ask. The interior oceans galore. Callisto has water. It's undifferentiated. You'll notice that there's an increase in differentiation as you go out. There's water and, you know, ice near the surface, and then a lot of mixed rocky material for Callisto. Ganymede's fully differentiated. The weird thing about Ganymede, of course, is that the ocean exists between 2 different phases of ice. In other words, you've got ice one on the outside, you know, whatever. So the ocean is suspended in a particular physiochemical hell. And so Ganymede's interesting. Remember that the JUICE mission for ESA has already launched. It has a radar on it. It's called RHIME. Our radar is called Reason. We work very closely with those guys, as you might infer from the names. And so it's on its way, and it will be orbiting Ganymede in the end. It'll fly by the system as well. Of course, our target is Europa. And the reason Europa, you know, that looks a lot like Earth. Basically, we have a metal core, silicate mantle, and about 100 kilometers of something that's water and covered by ice. And so if you're looking for an environment that can host things, the pressure melting point at the bottom of that ice shell is pretty much the same as Earth. I can point to a spot on the map of Earth where the pressure, temperature, and pretty likely the salinity of the ocean underneath it is more or less identical to Europa. Now, what you don't have is an energy source, and we'll talk a lot about energy sources here, but Europa is rich in oxidants because of the radiation environment of the Jovian system. And depending on how much energy gets into that silicate mantle, we may have a richness of reductants. And when you put those reductants together with those oxidants, that's the world of black smokers and all of that. And so we do okay. There is potentially sufficient energy to maintain moderately robust ecosystems. The amount of carbon goes back and forth. You probably read a couple of weeks ago, they're estimating the CO2 emissions from Europa and the hydrogen that's available for oxidants. So there's a lot of arguments about that energy balance, but it's looking pretty good. Okay, again, it's the outer layer of H2O. We're going to dive into that. The radar for Clipper was justified. Yeah, you know, I can tell the story here at UT, but basically Charles Alachi asked the radar science community, on the radar engineering community, and they go, "Oh, that's easy. They figured it out. Don't bother us." But he couldn't get any questions answered specifically about what he needed to know for these habitability problems. So he came to us, and we were able to answer the questions, and that was in the late 90s. And since then, we have taken over the science definition for the icy shell for Europa. I was in charge of that for most of 20 years. So here we are. There's the icy shell and the water. Let's just dive in and see what we got. Here's the first problem we have, and that is it's an icy shell. There's about 100 kilometers of stuff that's more or less the density of water / ice. Remember, ice is about 10% less dense than water, so it floats. And we either have a thin shell, a thin brittle shell, a few kilometers, with a lot of activity in the ocean and maybe a lot of activity in the silicate mantle. That's one end member of Europa. The other end member, which is probably the more likely end member, if you believe the inferences from the topography of the surface of the ice shell, that there's a few kilometer brittle shell overlying a ductile shell. And the ductile shell is 10 or 15 kilometers, and then it sustains convection. Now you go, well, what's the energy for convection? And the weird thing about convection on Europa is that the run through of the math shows that the thermal expansion of ice over the temperatures that are available in those convection models probably aren't enough to drive buoyancy. And that means that you've got exchange of impurities. And so for those of us who work on floating ice on Earth, that's not strange at all. You know, we have exchanges of impurities on Earth, and I'll show examples of that coming up. First half of this talk is basically, yeah, we'll get there. So that's the big question. You'll notice you have a complex and heterogeneous thermal environment. And so the wonderful thing is that ice is magic because it's a pretty much a perfect insulator when it's cold. And as soon as it hits the pressure melting point, it's pretty much a perfect conductor. And so if you're running a radar experiment that depends on the contrast of dielectrics, you can't make a material better than ice. There you go. There's my 20 years of justifying it to a community that's never done it before. It apparently worked. We have spent $250 million in pursuit of that. And we are there. I'll show some pictures at the end. That's just for the radar, mind you. The rest of it, you know, the rest of it's 10 times, 20 times that. So we have the 6-shell, thin shell model, which we'll get back to over and over again. The surface of geology. This is a Mercator projection of Europa with the anti-Jovian side up the middle. You can see the little dots here in the middle. We'll get back to those too. Those are blemishes on the surface that are important, that will be important. The most important thing here is that the endosphere seems to have sort of two modes. One is nominally the creation of crust, and one is the destruction of crust. So we have these chaos terrains where it's pretty clear that crust is being destroyed. Where it goes is a great question. And these rich plains, which is pretty clear that that's where crust is being created. Where it comes from is a really good question. You modulate that by the incredible, the magnetosphere of Jupiter is basically taking the tidal energy of Io, because the solid tides on Io are huge. The interior melts, it spews sulfur. That sulfur is ionized, it goes into a magnetic tube, and that plasma is accelerated. And so it's actually the trailing side of Europa. See the yellow? That's the sulfur from Io being plastered onto the trailing side of Europa, because Jupiter rotates faster and the magnetosphere slaps it in the back. And we have a little on the leading edge too. The red stuff in the middle is probably endogenic. So we have this balance of endogenic material and exogenic material across the surface. So it's the exchange between the atmosphere in the ice shell and the interior, i.e. the ocean in the ice shell. It's a big deal on Europa. The number one question that we have is we really don't know the energy balance for the system. In other words, the tidal deformation of Europa is huge. It's 30 meters, hypothesized to be 30 meters. It's all in the ice shell. And then there's a good chunk of that energy that goes in the ocean circulation, which is what Krista Soderlund does. And then we have no idea if the silicate mantle is as stressed as the silicate mantle is on Io. And so just balance those things in your head. You know, if that energy is going into the silicate mantle, then there's going to be lots of exchange at the ocean floor, papers galore on that. If that energy is in the circulation, then you're going to have a redistribution of impurities from the equator to the poles, the poles to the equator. There's two sides to that community, and that's going to drive the convection because when you melt ice off the bottom of the shell, you know that those salts go in, but when you freeze ice out of the ocean under the bottom of the shell, it's a distillery, 99% of the impurities are rejected. And so going back to the driver for those convective cells, and when you reject the impurities, you add a buoyancy factor. And so it probably requires rejection of impurities for upwelling warm. And then what goes up has to come down, which means the cold ice goes down. So you have warm ice coming up, cold ice going down. So you've got this balance of impurity loading and thermal loading going back and forth. And it's all, we believe, driven by accretion at the ice-ocean interface. So things that are important are the accretion of the ice-ocean interface, the behavior of the heterogeneous thermal environment, heterogeneous compositional environment in the ductile part of the shell, and then the brittle shell on top, and all kinds of crazy things go on in the brittle shell, which we'll show. And then interestingly, that near surface where Jupiter and Io are conspiring to beat the heck out of the top few meters. Remember, we had no capacity to say anything about the near surface below a few microns. And so our radar is able to do that. Okay, so the first part of this thing, what are we looking for in Europa subsurface and how do we look? I've given you a precursor of all that. So here you go. Here's those ridges we were talking about where crust is destroyed. Here are all the models. You mine the literature and you either have water working on cracks or you have viscous, ductile ice working on cracks. And there's always the potential for shear heating because you have these large bands that span almost hemispheres. And so there's shear heating there, water's available. And so there you go. Those are the models. You pull the literature and you can tell that a radar is going to be a wonderful test for this hypothesis, insulator over conductor. This one's a little bit tougher because you've got, a cold insulator over an impure, warmer ice load. So there's some problems with that. Here it should be pretty straightforward. I'll actually show an example of this one from Earth. So there you go. This rich formation hypotheses and kind of how a radar would work on this thing. This has never been done. But we do this on Earth all the time, but we have never done this extraterrestrially. I'll show some examples from Mars, but Mars is very different. Okay, here's chaos. Remember that chaos terrain? And again, it's the same. You either have liquid on the thin shell model, or you have a thicker shell model with ductile warm ice plume coming up and busting it. And there's an incredible variety of combinations of those things. We'll show our favorite. I'll show our favorite towards the end here. But you can see again that the radar is going to be a lovely hypothesis test for this one, lovely hypothesis test for this one, lovely hypothesis test for this one. This one's going to be tough, but we may be up to it as long as there's compositional difference between that warm ice and the ice above it, a dielectric contrast. Okay, this is a formality. These are the science requirements that we built this radar to. I'll go into the details. Let's go to the science requirements first, how this all shook out. These date back all the way to those science definition teams that were being discussed. But characterized distribution, any shallow surface water, of course, we write the things, they go to headquarters, and headquarters comes back with the word structure. Remember that wonderful thing I said about a perfect insulator and a perfect conductor? What's structure? Any idea? We didn't have any idea, so we had to invent that literature because we had to say, okay, the impurities are mobilizing, and then the impurities are going to do something. If they follow through the PT curve, then they're going to become something else. That something else will be structure. I'll show you a picture of that in a little bit. That was our biggest challenge, was water. Water is easy, structure is difficult. Search for an ice-ocean interface. I showed how difficult that could be. As long as it's clean water, that's fine. However, if we have this impurity exchange and it's warm at the interface, then all of a sudden you have a chance that you'll cross the pressure melting point, and you'll have brine. You'll essentially have brine pockets all over, and there's scatterers. And any person who knows anything about radar and light, those scatterers are just energy dissipators. So it could be problematic. So the idea is to get subsurface thermophysical properties along. we don't see a clean ice ocean interface, we should at least see a zone of altered subsurface thermophysical properties. Material exchange, I've showed you examples of how we test those hypotheses. We're not going to talk about a lot here, but we are the geodesy instrument for H2. We do the tides. There is no laser altimeter on Clipper. I didn't go through all the Clipper instruments. There are 9 of them. About half of them are in situ, half of them are remote sensing. We're the biggest, and we're half the data volume for the mission. Radar is very, very, very intense data volume wise. So the gravitational tides require that we get very precise surface elevations on repeat tracks. And there's whole talks that we give about how you do geodesy with long wavelength radars. It's very unusual. The mission had a laser altimeter proposed, but that laser altimeter was heavy and it cost a lot, and you didn't really need it for the magnitude of the tides on Europa, which are hypothesized to be about 30 meters. So these are big tides if the energy is dissipated in the ice shell. So it's the tidal amplitude that will tell us how much energy is dissipated in the ice shell versus the ocean versus the silicate mantle. And note that everybody wants to put a lander on Europa. It was not treated well in the last decadal survey for all the right reasons. We have a flagship mission going there. You probably should figure out what you've got before you invest in a lander. And we will, however, have to do the site selection for that. And Cyril Grima is doing that. Cyril's also in charge of the delicate negotiations between levering the JUICE mission to Ganymede's results and the Clipper mission to Europa's results. So that's here at UT. And we train virtually all of the graduate students and postdocs who will be taking over the tactical mission planning for this in the next 10 years. Those are all our people out there because they had to be tight. We were responsible for managing the engineering team. Again, it's about 70 engineers over 9 years. Yeah, and this is the details of the instrument. We have a VHF. Now I can point to the antennas and things. It's 60 megahertz, which is 5 meter wavelength, a channel 4 on your TV dial in the old days. And then we have an HF, which is 9 megahertz, which is 33 meter wavelength. And so the reason we have the 2 different wavelengths is that scattering is heavily nonlinear in frequency. It's up to the 4th power. And so if we do have these fields scatterers in the interior, it's really essential to have a long wavelength. The 33 meter, for range of the hypothesis for a porous ice regolith, the 60 megahertz in the worst possible case can lose 100 dB of energy. That's just a lot. But for comparison, the 9 megahertz with the same distribution of scatterers loses 1 dB. Orders of magnitude. And so that is why there are 2 frequencies. Why are there 2 frequencies? For that reason alone. The hypothesis testing for Europa requires that we're impervious to scattering, but we want the resolution of the higher frequency, high bandwidth systems, specifically to understand the brittle shell, and then the HF will give us a chance to get through the scatterers in the ductile shell. So sounding, the shallow is 3 kilometer target. This is what all those graduate students and postdocs were justifying. This is validating the model. In other words, can we test the hypotheses with these parameterizations? The answer is yep, we can. 3 kilometers shallow, 30 kilometers deep. So again, we can test anything to 30 kilometers. Doesn't mean we'll see it, but we can test it. Altimetry, we are the altimeter. We're responsible for H2, the tides. And so that comes up over and over again. There was no geodesy funded for this mission until just a couple of years ago. They brought a gravity team on. And so we had to hold down the fort for geodesy for 10 years, for 8 years, I guess. And then we've handed it over. Goddard's taken over again. Again, they were on the laser altimeter, but now they are going to use us. We invited them to join the original proposal, but they wanted to do laser and they lost. So now they're back and we're handing them our radar. It's all good. It's all good. It's a very friendly family. And then reflectometry is a weird thing that was basically invented here by Cyril Grima, but it's essentially using the near field effects of the coherent energy from the bulk dielectric properties over a wavelength or two of the radar versus the incoherent energy from the scattering field around it. You take the ratio of those, and it turns out they obey two completely different sets of statistics. You can invert those statistical distributions for the bulk permittivity over those two wavelengths. Think about that. Instead of 3 microns, we now have in ice, the 5 meter wavelength in space is about a 3 meter wavelength in ice, which means we have the bulk permittivity over the top 6 meters for the VHF radar, and we have the bulk permittivity over the top 60 meters for the HF. So we can compare those two, and we do this stuff in the polar regions right now. It all works great, and it's super sensitive to conductive impurities if they show. So if something weird is going on the surface of Europa, like that upwelling water hypothesis test, if that stuff can exist for a while and it makes it to the top 100 meters or so, we will see it. And then, of course, it shouldn't last long. It's 100 Kelvin at the surface, so it's going to go away. But it's very clear you can sustain fluids like that. Mark's here. You can sustain fluids like that for short periods of time. And if they exist, then we hope to catch them. We also have plumes. Everybody has heard about plumes on Europa. Remember that the plumes, the gravity on Europa is much higher than the gravity on Enceladus. So all the pretty pictures of plumes going out into space from the South Pole of Enceladus will not happen on Europa. Gravity won't let it happen. That stuff turns around and goes back, which means probably snows on Europa. Okay, and so when you think back to that reflectometry I was talking about, the plumes, the plumes come up, it snows back down, and if you have a regular driving function for that, you should end up with a layer of snow associated with the plumes, and then we'll have the bulk permittivity of that layer of snow and can test that hypothesis. And if it gets thick enough, then we can map it. If it's more than 100 meters thick, we actually see the bottom. There's a nice contrast. We see the bottom. So plumes and plasma are really interesting. And we are the plasma instrument as well. There is no plasma instrument, but our 9 megahertz is very, very much subject to basically to the ionosphere, to ionic impurities. Jupiter, and there's a lot of neutrals, and the ions don't do much above 40 megahertz. So our 60 megahertz is more or less impervious to the ionosphere, but our HF is hugely subject to it. And what happens is as you traverse an ionic medium, the different frequencies travel at different speeds, and so you have dispersion. The nice thing about it is you can take that dispersed waveform and invert it, and it tells you what the total electron content is along the path. And so that's how you do plasma sounding. And so our HF is a plasma sounder at megahertz. And so we have the only plasma. There's a plasma instrument, and a local plasma instrument on the spacecraft, but they have no idea what the stack of plasma is between them and the surface. We measure the stack of plasma between them and the surface. Of course, we just get a bulk number, and they get a specific number, but for hypothesis testing, that's perfect. So that's the distribution. The HF does everything the VHF does, but a much lower resolution. We're launching in October. Jupiter orbit insertion is 2030. That's everything on this slide. Let's just keep rolling. Is this going to work? Here is a 2-frequency radar compilation for Mars. This is the Mars North Polar Cap, and with 2 flights over it. The Mars radars were built by the Italians, and Picardi was building a plasma sounder, and he was justifying that at the same time we were originally justifying the radars for Europa back in the late 90s. He didn't tell anybody he was going to sound the ice on Mars, and so basically he took a plasma sounder. It's the one on the bottom here. It was at 1 to 5 megahertz. Then they flipped it around and they sounded the North Polar Cap of Mars. And you can see, boom, they got right through it. It's 3 kilometers, looks gorgeous. Based on that success, we we were having a much harder time convincing people we could do radars in the outer solar system. And he snuck this one in at Mars. It was great. It was so successful. They built another one at 20 megahertz. So we have an HF and a VHF radar flying around Mars. They're still going. And you can see that the resolution is much higher with the VHF. It's 10 megahertz bandwidth. The interesting thing is that, just like we said before, you'll notice that the long wavelengths penetrate the scattering at the base of the ice sheet on Mars. And here's that same boundary, and the shorter wavelengths do not. They scatter off of that interface. This is an earlier, dirtier ice cap, so there's much more, scattering energy in it. But this basically validates the two-frequency approach for testing hypotheses in a scattering medium. So that's what we got, and you can see blow-ups here of the fine resolution for Charade and low resolution for Mars. Give away the resolution, you get through it, get the resolution back, and then you cross your fingers to get through it, but you're covered if you don't. As long as you have two frequencies, that's why we have two on Mars. I basically gave my life to keep those two frequencies. I had a post-it at NASA headquarters on the 8th floor that said, remove a frequency 9 years ago. And I talked and I talked and I talked just like this. And at the end of the day, that post-it was pulled down. And so we kept two frequencies for Clipper. It added a lot of expense, but whatever, we're here now. Okay, how do we go about doing this? Is the Earth worth anything for helping us decide if we're going to test these hypotheses? And this is that north pole of Mars with the layered deposits that we just saw at exactly the same scale as Thwaites Glacier in West Antarctica. This is what fly a lot of airplanes. Thwaites Glacier is the Doomsday Glacier you read about. It's the one that's bottom. You can see it right here. Here's the ocean out here. This is grounded, bottom's well below sea level. So humanity is studying this inverse slope like crazy, because if that grounding line hops over this little impediment right here, there is nothing holding this ice sheet back, and it's 1 to 3 meters of sea level, depending on who you believe. So we get a fly over this glacier a lot. So things like this. The wonderful thing about Thwaites is that it's grounded like Mars. It's wonderful, but it also has a large floating tongue, very dynamic floating tongue. So all the hypotheses for the floating brittle shell on Europa, we can test on these floating tongues. We can test on these floating tongues around Antarctica. Okay, here's an example of how we can use Antarctica to basically validate the models for Europa. Here's shallow subsurface structure. You need surface elevation as well as ice thickness. Here's the biggest iceberg that broke off while I was working in Antarctica, B-15. You can see how this is a small slice of it left, but it was giant. It was 50 kilometers long or something. And so anyway, you can tell that just seeing a shiny surface doesn't say there's water. If you're going to definitively determine there's water on Europa, then whatever it is you see has to be floating. The only way you can tell if it's floating is if you get its ice thickness. It should be shiny. It doesn't have to be shiny. It can be rough on the bottom. This one's got crevasses all over it. But then you need a precise surface elevation. And then you can use the surface elevation above hydrostatic and then the thickness to see if you obey Archimedes' principle. And if the low surface elevation corresponds to the low thickness, and the high surface elevation corresponds to high thickness, you're floating. We have to use that on Europa. We can't just use the character of the return. We're having nightmares on Mars with that. If you've read anything about the subglacial lakes in the Mars polar caps, it's all one end arguing they're shiny, therefore they're lakes. The other end is arguing that lots of things are shiny. They're not necessarily hydrostatically stable. And so that's the argument that happens on Mars, back and forth. And we're on both sides of that argument because we need to understand both. But in the end, if it doesn't obey Archimedes' principle, it's not floating, and you can't prove there's water. This is what I was talking about with that reflectometry. This is us doing it over the only ice shelf on Earth that basically is created from ocean freezing on the bottom. It's about 50 kilometers long. It's McMurdo Ice Shelf. It's where they land all the airplanes from McMurdo Station in the old days. And so you can see that when you look at that integrated, you can look at those integrated properties over a couple of wavelengths, and these are the bulk, the color map here is the bulk permittivity. And this is porous ice regolith with low porosity, porous ice regolith with high porosity. This is clean ice. In other words, it has a perfect permittivity of clean ice, no regolith at all. And then over here, this is where the ocean, the edge of the ice shelf is dipped below, it's dipped the regolith below the sea level, and the ocean is actually infiltrated. And you can see that the permittivity jumps over 10. So if you have a brine penetrating the porous ice regolith, this reflectometry, it's literally a stoplight. And so we'll carry this to Europa. It will work just fine on Europa. And then we have dirty ice over here that does the same thing. You get these intermediate permittivities. There's some mixture of ice and dirt. This is going to matter a lot on Ganymede because Ganymede has all kinds of surface wasting. It's very, very strange. And the distribution of rock debris from the surface evolution of Ganymede is really important. This is just a reminder, we are doing that. This is Marsis at Mars mapping the total electron content, just like we're going to do for Europa. This is the night side, there's no ionosphere. This is day side, there's an ionosphere. It gets worse as the sun angle changes. Same thing on Europa for our HF. So this is the world we have. It's hugely valuable. And remember that we have to get super precise altimetry. And believe it or not, for geodesy, even our high frequency, 60 megahertz, has a small correction for the ionosphere. So we'll use the HF to establish that correction, apply the correction back to the VHF, and we will be as good as a laser altimeter for types that are that big, that are uncertain. Okay, so this is what we're looking for in the subsurface and where do we look on Earth. This is how we look on Earth. We've been building a fleet of airplanes for the last 15 years. This is the first one we started 15 years ago with Australia and the UK. The United States wasn't interested, but we have 60 megahertz radar hanging underneath the wings. We were funded by the state, believe it or not, the US State Department, the UK Foreign Office to work with China to build this airplane. So it's still flying. It's just a little harder to work with these days. It's a gorgeous airplane though. And then this is the one NSF has finally come back and said, oh my God, we've lost that capacity. So just in the last few years, we've put an airplane together for NSF. Now this airplane has two frequencies. We can't do the 9 megahertz. The 9 megahertz on Earth is the emergency communication frequency for naval aviation. You don't do 9 megahertz. However, we can go the other way. And so we have two frequencies, one is now higher. And so we have an array of 600 megahertz antennas under this airplane. So we have a ratio of 10. And so so the nice thing about going higher frequency is that we can scale the elevation. So we can come down to something humans can survive, fly up with the two frequencies and the ratio of the scattering on those two frequencies. In other words, in that case, the 60 megahertz pretends to be low frequency, and then the 600 megahertz is the high frequency. And so we could test all those scattering hypotheses with this aircraft. There's some places we can't get. Plates Glacier is a nightmare to get to. So we've transferred all these instruments. We transferred the testbed Europa radar onto a helicopter, and we fly it off the back of a Korean icebreaker. All 4 of these platforms were flying this last season. We had 4 expeditions go at the same time, testing different places. And we'll take a look at these places. This is all grounded ice. This is the subsurface of Antarctica. And the scale on here, it's about 5,000 kilometers across. And then the goal here, of course, you can see where our plane flies. So in these big lowlands, that's where sea level risk is the highest. But the most important thing is every one of these big basins goes afloat over the ocean. So these green circles are where the ice shelves are coming off of those main basins. And then all of those brittle shell hypotheses are testable in the green spots. And you can see then China's flying over here, Australia's flying over here. We're in the interior. We're working on ductile processes in the interior and brittle processes. And then here's Plates Glacier out here. So we have all these different experiments running specifically for sea level, but oddly enough, the processes and the physics of it are the same as the things we're testing for Europa. So we can do them both at once. Okay, let's just go back and make sure we did a good job. We've got about 15 minutes to get through. This is Thera and Thrace Macula. These are typical chaos zones. This is a cartoon we put together for a Nature paper in 2011, showing that these things are more likely the product of a perched water system. And so we'll go through that in just a little bit. So you don't have to believe me here. We'll get to it later. But this is a cartoon. And then you take a picture of the chaos on Europa, and then you take a look at those icebergs that I just showed you before. So basically, if Thera Macula creates a perched water system, which breaks up the surface, which has floating icebergs, those floating icebergs have to obey Archimedes' principle. We've proven the hypothesis. So that's our attempt. That's an example of how we're going to do this. And remember, our number one science priority is shallow subsurface water. So that would get us there. So altimetry is always important. Sounding is great. It's beautiful, makes great pictures. People publish Nature papers off of sounding that isn't physically realizable. Archimedes' principle is physically realizable. Get the altimetry, you get the radar, you're good. You have truth in nature. Okay, these are those ridges. Here's Europa. And here you go again. Here's a model, one of the models. It was the one over on the right that I showed before, of a water sill based where water is collecting due to transform faulting underneath the ridge. You get flexural bulges, all kinds. Could this possibly exist? It does in Greenland. Okay, so here is a double ridge in Greenland. It's just a double ridge. You look at it, well, how did that happen? That's not Europa, it's nothing. But believe it or not, the physics are incredibly similar. Here's the blow up of the radargram. Again, you see porous firn, porous ice regolith, and then you see a water table, perched lake. And then what happens is that it leaks out into this porous ice regolith and refreezes. And then here's a cartoon of what's going on. That perched lens basically starts freezing out, but then it expands. And then it builds a plug, it freezes close, and then that plug is driven up, and then you build a double ridge around it, both tectonically and then through mass wasting of the double ridge. That was that hypothesis for Europa. It's going on in Greenland. Now that this water did not get there the same way it got there on Europa. We're starting with the water lens. Here it was water collecting on the surface elsewhere and pouring into the fur and then collecting. On Europa, it's a diapiric plume coming up, melting the overlying ice, and then the brine pockets coalesce into a lens. So basically, we can test this hypothesis as well. If you look really close, you can actually see the plug coming up and the two ridges. It's gorgeous. This Dusty Schroeder's people. He came through here working on Europa, and now he's got tenure at Stanford. So we're doing right by the children who come through. Okay, searching for the ice-ocean interface. I described how complicated this is going to be. The thin shell should be easy. We're not going to be that lucky. There's no way we're going to be that lucky. Thick shell, yeah. And the question is how you characterize thermophysical horizons. The only thing we can do right out of the bat is take whatever we think is the ice-ocean interface, use the surface elevation, use Archimedes' principle to see if the thin shell is holding water, literally. Being held up by water. And so that's easy, not a problem. However, when you go to Earth and you start looking at places like this is the Filchner-Roney ice shelf. And here's cross-section of the Filchner-Roney ice shelf. Here's the ocean. Here's the ice-ocean interface. It comes through. And when they picked the bottom of the Filchner-Roney ice shelf, it was pretty thin. And then when satellite altimetry came along, they did Archimedes' principle on it, and it didn't work. In other words, the surface elevations of the Filchner-Roney ice shelf did not match the thicknesses that they were measuring for the ice shelf. Then they finally got through it, and this is what they found. It's a layer of marine ice that had been frozen onto the base of the ice shelf. So what they detected, right back to what I said before, the hypothesis test, they saw this thing, they said, that's the ocean. Let's publish papers like crazy on the thickness of the ice shelf of the ocean. You come along, you do the altimetry, wrong. And then, however, it's good news because then you get this water ice and you can say, hey, let's take the altimetry, do a 2-layer model, make the top pure ice and the bottom impure ice, and then let's do a contour map of the marine ice plated onto the bottom. That's what this is. That's a contour map. It's 400 meters of marine ice plated on the bottom of the ice shelf. Okay, we can do that on Europa. Again, if we have altimetry, if we are immune to scatterers and actually can see through this thing, and so we've got a really good shot of testing those hypotheses that way. Okay, now it's the exchange thing. I'll start with atmosphere because it never gets enough attention from us because we're not plasma physicists. But everybody's seen the Hubble's got them now, but these UV images of it's hydrogen emanating from. Now the problem is it came out of the South Pole, so everybody said it's Enceladus, but no, they're all over the place. They're incredibly rare. They don't happen very often. They may not be real. The signal noise is about 1 on this image. So, but they've occurred enough that people do believe that something is emanating water. Okay, now is that coming from the, if you're a thin shell person, that's coming from the ice ocean interface. Okay, if you're a thick shell person, this would be coming from the perched lakes. In other words, the perched lakes are freezing. You saw the map, perched lakes are freezing, cracks above them, the water spews out. And so that will contribute to the compositional impurity, which is why you have in situ instruments flying through those plumes to get that. And then that's neutrals coming out for the most part. And then we're flying along doing the plasma. And so we have a ratio of ionized stuff to neutrals. So we can come through and say, are those really neutrals coming out? Whereas the particle instruments only can say that up where we are is all ions. And so, so we'll be able to test the atmospheric exchange, not to mention what I talked about before, where if it snows back, then we could look at the properties of the porous ice regolith to see if there's a layer of snow centered on the source of plume. Late to the game, Applied Physics Lab at Johns Hopkins has been looking, a woman named Louise Proctor, who's their chief scientist, loves Europa. She gave a keynote at LPSC last week, and they have been looking at the old Galileo images and have found missing crust. In other words, we have subsumption. That's the word that geophysicists use. So we have subsumption on Europa. So crust on the surface is going down. And so this is their cartoon. I don't believe it for a minute because they're using porosity. Everybody knows that it takes a density contrast for things to go down. And on Europa, all you have is a porous ice regolith that its porosity is dictated by radiation gardening from Jupiter. No, it's going to be really hard to do that. Something else is going on. But basically, subsumption occurs. So the question is, can we look at these kind of things? We don't believe this model at all. And it's been JPL's in love with it, but right now we can't find a reason for it to work. So anyway, go to Lake Vostok, the biggest subglacial lake in Antarctica, and we did this here ages ago with a bunch of high school kids. But this is Lake Vostok. Remember what we said about shiny is a lake? Boy, that looks like a lake. We didn't have altimetry until 1998. And we finally got satellite altimetry, and we could prove that the shiny spot was indeed a float. Now you can see all of this wonderful stuff in here. And believe it or not, these are impurities, these are acid impurities added from volcanic eruptions, volcanic eruptions that are represented in the stratosphere. So all this stuff is easy to see. That's not what we're worried about here. What we can see is that this lake is freezing and you have accreted ice returns. And then you can actually, if you've got a fleet of undergrads, say, hey, go pick all these accreted ice returns over this 300-kilometer long lake. And they did that. Here's the coastline of the lake in white. And here's what they picked. And basically what you're seeing is that these accreted ice returns are actually ice is flowing from the left to the right on the ice sheet. So it's moving this way. And all this accreted ice is being run up over the bounding mountain range. And when you look at it, that is the kind of thing. It's coming up and over, and we expect to see something like this on Europa going over and down. And I think it's going to be impurities. I doubt that it's going to be a porosity difference. But whatever, we will test both hypotheses with complete fairness. So that's it. So we will be able to look at these be able to look at these subsumption terrains. Okay, chaos, bringing it in for landing here. This has been inferred so far, and basically back in 2011, we published a paper in Nature on these perched lakes. And essentially, it takes the warm upwelling diapirs, and then if you're upwelling into ice with higher impurity load, remember these are fresh. The only buoyancy you get is from deleting impurities. If you're coming into ice with impurities, you're going to reach the pressure melting point for that ice. The planetary community thought all that water went down because water is heavier than ice. The trouble is, if you're a glaciologist, you know that the water goes wherever the surface slope sends it. And if you see this surface slope, you know the water's going in. And so we hypothesized that these upwelling diapirs would be characterized by water lenses sitting on top of them. And then and then these chaos zones were crazy because they had a characteristic that the matrix between the big blocks was higher than the blocks. And Archimedes would go, okay, well, one, it's not floating. And so this is not floating. However, we hypothesized we could find one where the inverse was true. And that is Theramacula right here. And so you can see this here. Here's the edge of the lens we hypothesized. You can see the boundary fault. You have a coherent ice lid over here. It's starting to break up like an ice shelf. And then if you break up an ice shelf in Antarctica enough so that the fractures are less than the thickness, they all fall over. And when they all fall over, they all crush. And when they crush, it releases the energy of an H-bomb. So it's this unbelievably high energetic source. And that seems to be what's happening here. And so you end up with a matrix with a few bergs in it. And the bergs are high and the matrix is low because the matrix is saturated. The bergs are pure ice, the matrix is saturated with water. So it has an intermediate density between the water and the bergs. And so that's the logic, and the hypothesis test was true. The neat thing is this seems to be the old end, and you can see that it looks like that the water is starting to freeze back out. It looks like the brine has been blown out of the central lens into the porous ice regolith, and then the elevation is starting to come up. And so as the water goes in there, it's being pushed out. It freezes in the porous ice regolith and it raises the elevation. So we had 8 criteria of paradoxes for chaos, and we checked the box for every one of them with Theramacula with this hypothesis. Connemara's old and dead, and it's a refrozen lens. The brine's high, the bergs are low. You can see it, and it's just there. And then the big question is this last slide on science. What happens to the water in those lenses? If the system is closed, like we had for Theramacula, then you only have the salt that you derive from the country rock around you, and then it's transient. That plume comes up, that diapir comes up, it loses its heat, and then you start freezing out from the top, and you precipitate out all the salt. So we anticipate salt layers at the bottom of these. Can you say structure? So we're just submitting papers at GRL on how you tell what kind of ice shell you have based on the thickness of the salt layer and whether we can detect it or not. So basically, if you're deriving the brine and the lens locally, the layer is thin. If you have a crack going all the way through, you're accessing the ocean. You're accessing full impurity water body as opposed to a distilled water body. And the layer should be a lot thicker. So we anticipate these salt layers all over the place. So we'll see how that plays out. And this is Brittany Schmidt, one of my other postdocs. She's just got tenure at Cornell. And so anyway, these are Brittany's students. So all these kids are in there chucking right now. It's kind of great. We've got a pretty solid community. They all talk to each other. It's great. Okay, again, I didn't want to ignore it, but we do have these tides. We have no idea. The biggest unknown is the distribution of energy between the ice shell, the ocean circulation, the silicate mantle. And then it's super important if we do have, if we do have active magma systems or we just have brittle fracture in the ocean floor, it's huge impact on the astrobiological potential, largely based on how much hydrogen is available. And Elizabeth Spears is probably listening. She works on that. So that's kind of it. Go to the next one. This is what you'll see, since we're coming into launch, this is what you'll see, you know, the press releases and everything that, you know, habitability, and you'll notice our stuff is kind of important as you go through all this. You need water, energy, and chemistry. Europa have a global ocean, lakes sitting in the ice. That's easy to talk to the press about. Chemical disequilibrium. Well, you've seen black smokers. Do we have them? And then what does it take in terms of surface oxidants to take the reductants and turn it into let's just call it a pressure for the existence of life. Europe's probably been stable for at least 1 billion, if not more years. So if we have life, if we have the ability, informatics, you know, they can communicate with private evolution of some kind. You know, it's had a long time of stability. And then don't ever forget that we have 5 years while we're getting to Europa. We will be traversing Antarctica, trying to figure out better ways to figure out how thick the ice shell is. Liquid water exists on Europa, the ocean interact with the ice shell. Geologic activity, can you say subduction, and the energy budget. Finishing this thing up, this is where I was. I gave a talk in this room in April of 2015. And 3 years later, you know, that was 2 months before we were selected. 2 years after we were selected, this is the cartoon history of reason with all things. And then here it is 2 years ago, we're testing the antennas, we're putting the instrument, the engineering instrument in TVAC. Then a year ago, this flight system all built and ready to go. Don't worry about it, but it's no longer a cartoon history. It's real, and this is over the summer. This is us being bolted to the door of the vault. Vault doors being closed. They've wrapped it up. We've done the EMI tests. We've done the thermal vacuum tests. It's been pulled out. It's being packaged over the next 6 weeks to go into a C-17 and fly to Kennedy. And our antennas are already in Kennedy, and they got installed in the solar arrays that were coming from Europe Friday. So there's a lot going down. That's it. Thanks a lot.
I think that someone's gonna be coming in here in 2.
In 2 minutes.
Yeah, we got, yeah, at least I finished in time.
Yeah, so we maybe have time for a question.
A single question.
Yeah, if you're online, feel free to ask, but it'll kind of be whoever gets there first.
That's a lot.
Some odd people online.
What's that?
There were 30 some odd people online.
Oh, wow.
Yeah.
I hope it was nobody from JPL. I always end up.
Unless they got the link from someone at YouTube.
Yeah, who knows? Maybe not.
So the only, your worry of scatterers, you think you got handled, the worry of ice, of it being thicker than not, you think you got handled? Do you have any other fear in there that is creeping out there that could be?
That the antennas don't deploy?
Yeah, okay, that's good.
Yeah, and remember, the antennas did not deploy for Ryan.
Oh, yeah.
Yeah, they halfway deployed. And then they had to use the first month of the spacecraft maneuvering to shake them loose. And then, okay, to finish the story, then they had to point it towards the sun to warm up a piece to basically make it smaller so they wouldn't get interfered with the deployment. And that worked. But that took a thermal engineer. And you know the layoffs at JPL 2 weeks ago? They laid off our thermal engineer.
Oh.
Little things like that, okay?
Got it.
And so now we're back in the mode where we're launching. We don't know if the antennas they don't deploy until after launch. We've done them individually, but not out on the basketball court size solar arrays. And so that's where there you go. That's it.
That's probably.
You know, that is totally it.
All right, I think we have to vacate the room, but thank